Okay, so the last class, ma'am, you had a few questions. So regarding the textbook which I was referring to, so I couldn't get the other one. One book that I could recall was Electromagnetics by J.D. Cross. So I'll write in the chat over here. So that it was one of the books which Professor Udaya Kumar from IISc referred to in his course in his course electromagnetism. So he had actually covered some questions and some examples on image theory where we had PEC and charge and I can't recall whether we had the line currents as well. So he had covered those things and he was mostly following this particular textbook. So I couldn't get time to again go through the book and find the chapters where it was there. But maybe if I get time, I'll share the page numbers and chapters as well. Um, and some other questions regarding being beta equal to zero and things. So I'm sure it will be covered in coming few classes. So, so maybe okay, then we can start now. So there are at least two people. Okay. So, so these informations we already have seen quite a few times. Again, we are back to Podzar, and we'll finish transmission line theory today and start with transmission lines and waveguides. So we'll look at T mode, TM mode, TM mode, and similar things in coming classes. So today we'll just look at the bit on the history part and some a few slides on the starting slides, but we'll properly start in the next class with the analysis of TMT and TM modes. So in the last class, we finished Smith chart, and let's do a quick recap of the okay. So the last class we covered we finished the Smith chart and the quarter wave transformer. So we'll do a quick recap of what we looked at. So we looked at the quarter wave transformer using two methods: the impedance viewpoint and the multiple reflection viewpoint. So so in the impedance viewpoint, we took the circuit and calculated the input impedance at this point, and then we had inserted this particular transmission line section which had an impedance Z1 and its length was lambda by 4. And by substituting this particular length over here, we found out that this tan beta term, the argument of tan. Turns becomes pi by 2, and taking limit we get this particular expression where the input impedance is equals to z1 square by rl the load impedance. And if we wanted to make reflection coefficient equal to 0, we must have this input impedance equal to this characteristics impedance of this particular transmission line. So we make them equal, and doing that we substitute the value of Zn equal to Z naught and then calculate the value of Z1. So using that, we get this particular expression, and we should note that this particular technique only runs for the multiples of a particular frequency at which we are looking for which this section is lambda by 4. Now, we also looked at this particular example where we plotted the normalized the deflection coefficient with the normalized frequency. We again so we found out this Z1 over here using the information given. We had the characteristics impedance and the load impedance. We found out the impedance for this value, and then we substituted instead of just putting the value. Okay, so we replace the lambda with the it's frequency, the frequency at which this particular lambda is, and then we wrote down the expression for reflection coefficient in terms of the frequency and the nodes, and then we plotted the this particular graph, and we saw that the reflection coefficient becomes equal to 0 for f by f not equal 1 and f by f not equal to 3, and similarly this goes on. So perfect matching is achieved only at the particular frequency f for which the argument of tan term comes out to be pi by 2. Then using the multiple reflection viewpoint, what we did this time was we did not use the formula for input impedance. We what we did was we assumed that a wave is traveling, and we found out the reflection coefficient and transmission coefficient at these 2 points. And using that, we first wrote down the expressions for the reflection coefficients and the transmission coefficients, and then we calculated the total reflection coefficient by this expression where we know that this particular if the wave is incident at this junction, it will some of it will get reflected, some of it will be transmitted. Again, at the second junction, it will be reflected, and at the again at this particular junction, some of it will be transmitted and some of it will be reflected. So this will account for this term, and the negative sign comes due to this total length traveled is lambda by 2, so it accounts for the phase as minus over here. And similarly, the this particular term is again calculated for the wave moving along this line. So using this, we'll get this particular expansion, and this can be again written in this form, in form of using a summation. And this summation can be evaluated using this formula that we have seen for infinite geometric progressions. And using this, we can again write down the expression for the reflection coefficient. Now, to make this reflection coefficient at this the total reflection coefficient equal to 0, what we need to do is we need to make this term 0, and this will become 0 when the numerator over here will become 0. Now, this numerator can be evaluated again. So we substitute the values of the reflection coefficient, transmission coefficient inside the numerator, and then evaluate it so that we get this again this particular fraction. And uh, to get this numerator 0, we have to make this numerator 0, and this will become 0 for z1 equals root under z naught RL. So this result is same as the one which we achieved in the previous case using the impedance viewpoint. So hence for this particular impedance value, the reflection coefficient will be 0 and the line will be matched. So any questions from the previous class, or we briefly discussed the quarter transformer, and we'll start with some more topics today. So we'll start with lossy transmission line. But before that, if you have any questions, maybe we can take that now. Okay, great. Okay, so we'll start with the lossy transmission lines. So up till now, most of our formulations involved transmission lines to be lossless. So we were considering alpha equal to 0, and also we considered R and G equal to 0. So in the initial classes, we saw that R and G account for the losses, and hence we can definitely approximate the transmission line to be lossless, as they have very low loss for especially for smaller lengths. So, but now we although in the Smith chart we have seen how to account for the if we have alpha non-zero. So we'll just look at the some basic formulations for low loss line, and we'll also look at bounce diagram today. So okay, so This is the general expression for the complex propagation constant. Gamma is written in terms of R, L, G, and C. And again, we can rearrange this to by taking out J omega L and J omega C to so that we have this particular term separated. Now we can take these terms, take j omega out of the this square root and write this term as root under LC. So this term becomes familiar to us. This is beta or the for the this is the propagation constant for the lossless case. And now again we are left with this particular term over here. Now, considering a low loss line, we mean that R and G have smaller values, so we can use that to use that to do some approximations. So, for a low loss line, what will happen is R can be assumed to be much smaller than omega L, and similarly G can be assumed to be much smaller than omega C. Now this again implies that the product of Rg will be much smaller than omega square Lc. Now using this approximation, we can remove this term over here. So this term will be much smaller than one, and this particular term over here. So we can remove this. So and we'll end up with a propagation constant looking something like this term over here. Now again, we can use the Taylor series expansion for root under 1 plus x, which approximately gives 1 plus x by 2 plus some other higher order terms. Um, Using this expansion for that using the Taylor series, what we can do is we can remove this square root and write this term over here. Okay, so this 1 plus x it turns out becomes 1 plus x by 2, and we ignore the higher order terms. And similarly, so the square root goes away, and we have this j by 2 over here. So this is the propagation constant for a low loss line. And from this, we can now separate the real and imaginary part. So as it turns out, alpha comes out to be half r by z naught plus g z naught, and beta comes out to be omega root LC. So this remains same as as in the case of the lossless line. And Z naught again, we are using Z naught term over here, so which means root under L by C, and this is the characteristic impedance for the lossless line. So in the absence of loss, this was the characteristic impedance. So we are using this in this expression over here. Now, using the same approximations, what we can do is we so we again we had the approximation R is much smaller than omega L and G is much smaller than omega C. Using that, we can like ignore these terms R and G. So we end up with the characteristics impedance equal to root under L by C. So again, the characteristics impedance can be approximated to be same as case of the lossless line, but the propagation constant will have some attenuation constant again. So I hope this was okay. If do you have any question? If you have any questions, maybe we can take that now. Otherwise, we'll move forward. Okay, so all these expressions, so all we are doing is that we are using these approximations and performing mathematics on the already known values. So these expressions won't bother you much in your exams. So essentially, what you need to do is remember only this expression. And if you are given the values of R and G, just put them, use a calculator and solve it. No need to stress about it that is it small or not, and like do I use the this more complex formula. So just put the value, solve it, and if you can recall, or if the formula is already given, then you can use that. So all these things you should know, but all you need to do is remember this formula over here. Now, another important thing that comes very often is what we here is called a distortionless line. So we'll look into this. So in this expression over here, the propagation constant, so this is the propagation constant for a lossy line, and the phase term is generally complicated function of frequency omega when the loss is present. So if you directly try to expand this, if just like using Taylor's or some expression, so this will become very complex. So both the imaginary part and the real part for this gamma will be very complex, and it will be a function of omega. So it will be a function of omega, omega square, and higher order terms. So this implies that beta is not a linear function of frequency unless it is a lossless line. So a lossless lines assumes that beta beta can be given of this form. It's a linear function that beta is some constant times omega. But if it is a lossy line, and what will happen is beta will not you cannot express beta using this particular in this particular form. So if beta is not linear, then what will happen is the phase velocity will vary with frequency. So this again for every frequency, if you try to substitute, if you have your beta as a linear function, so if you substitute this beta over here, what will happen is the omegas will get cancelled, and you will get a constant value for all frequency. But if beta has higher order terms of omega, so what will happen is the phase velocity will be dependent will become a function of frequency, and and when this happens, the different the waves of different frequencies will travel through the medium at different velocities. And now when these waves of and when these waves different frequencies travel with different velocities, if you send them at particular time t naught, what will happen is when they after some time, these waves will arrive at different instants at the receiver's end. So what and this phenomenon in which the different the waves of different frequencies travel with different velocities, and they separate from uh, and they get separated, we call this as dispersion. What happens is you get a distortion in the signal which you are trying to send. So and this dispersion thing is generally an undesirable effect. So we do not want dispersion, and so hence uh, so we do not want dispersion, and and a lossy line will show dispersion. But under one circumstance, this the what will happen is even though the line even though your transmission line is lossy, it will not show any dispersion if we try somehow, if we get the beta as a linear function, but R and G are not non-zero. Uh, RNG are non-zero. So and again, this dispersion thing comes into play when your transmission line is long. If it is short, then again this dispersion will be very small, and your signal will be intact. But if the transmission line is very long, and even if it has slight loss, will have and if the propagation constant is given by this expression over here, for a very long line, what will happen is that after every distance, the this uh, the separation will become greater, and hence the dispersion will be more, and hence the signal will be more distorted. Now, a special case, as I was saying, that we can have a lossy line, but again, the propagation constant, the beta in the propagation constant will be a linear function of the frequency, and this happens when you make R by L equals G by C. So, if the ratio of R and L, if it is equal to ratio of G and C, what will happen is that we will have omega beta as a linear function of omega. So we'll see this. So using this relationship R by L equal to G by C in along with the propagation constant, we will substitute this into this. So what we can do is we will we substitute G by C by R by L. So we take these terms common out. Okay, yeah. So we take the term C as common over here, and we substitute G by C as R by L. So what we get is this term over here. And again, since this is a low loss line, okay, no, sorry. So this term turns out to be a perfect square. So we can replace the square root and solve this and to get this particular expression over here. So what we see over here that if we multiply these terms, so we get alpha as r root over c by L and beta as j omega root under LC. So again, we can see over here that beta is only a linear function of root under L by C, although r and g are non-zero. So in this, so this is a special case where you'll have losses, but your signal won't be distorted. This shows that beta is equals to root under beta is equals to omega root under LC, and this is now a linear function of frequency. And again, this also shows that alpha does not depend on frequency. So the attenuation constant is now not a function of frequency for this particular case of distortionless line. So this also implies that all the frequency components will be attenuated by the same amount. And again, so the distortionless line is not loss free, but is capable of passing a pulse or a modulation envelope without any distortion. So any signal that you're sending, it won't be you won't see any distortion in that. Okay, any questions? If maybe you can raise a question, tell the question, or you can write in the chat. If not, maybe 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 forgot to turn off their mic. Okay. So if you have if you have a question, you can unmute yourself and ask, or otherwise you can also write in the chat or raise your hand. All these options are there. So a little bit of history. So this case of distortionless line uh, was actually developed by Oliver Heaviside. So we have seen this photograph earlier when we were discussing Maxwell's equations, and so Maxwell had given whole set of uh, a number of equations around 16 or 20, something like that. And Oliver Heaviside was the person who used who combined the equations using vectors and things to get the famous force Maxwell's equation. So Oliver Heaviside has done a lot of work in electromagnetism, and this concept of distortionless line was again given by him. So, okay, maybe we can take a pause over here and take any questions that you might have from the distortionless line and the low loss line. So in the low loss line, we assume that j omega L, so the R is much smaller than j omega L, and G is much smaller than j omega C, and we use that concept to simplify the propagation constant over here. And in the distortionless line, we use this particular relationship R by L equal to G by C, and then again we evaluate it to get this expression over here. So so far, just two different cases of approximation to get set to get some equations which allow us to get some insights on the wave propagation in the transmission line. Sorry. If no questions, we'll proceed to another case. So we have seen low loss line, distortionless line. Now, what if the lossy line is terminated? So we've already seen cases of terminated lossless line, and under different circumstances. For example, some load ZL, some ZL equals Z naught. Now the ZL is open circuit or a short circuit. So all these, the observations again over here will be analogous, and the only thing changing will be some portions of the formula. So this particular figure shows a lossy line terminated with load ZL, and we now uh, have the propagation constant having attenuation constant as well. So the gamma is given as alpha plus j beta, and now this is complex, and but we are assuming the loss is small, so Z naught is approximately real again. Now, the expression for voltage and current wave for the lossy cases, they can be written like this. So earlier we had beta over here, and now we can directly write gamma over here. So the expression remains similar. So and this gamma term over here, and if the this transmission line becomes loss free, so where we have the attenuation constant equals 0. So again, this particular expression relationship will become same as the lossy case, where we'll have beta instead, j beta instead of minus gamma. Now, and again over here, the this gamma is the reflection coefficient, and V naught plus is the incident voltage amplitude, which is referenced at z equals to 0. Again, similarly for the reflection coefficient at a distance L from the load, so we instead of beta we substitute gamma, and then if you separate these e power terms as products, so we have okay, so we end up with something. So this is the final expression over here. So uh, this is the magnitude term, and this is the phase term, where this beta term is changed by this attenuation constant is included. So we have a gamma over here. So the expressions remain similar, just replacing j beta by gamma. And similarly, the input impedance at a distance L is again, these expressions remain similar. This instead of using tan J beta L, we will use tan H gamma L. So a slight change over here. So this part remains same. Instead of using tan J beta, we're using tan H gamma L. And if for the special case of lossless line. So this gamma will become J beta, and this J beta uh, tan complex input to this tan H will evaluate, and you'll get back to the tan term over here. So maybe you can look into the trigonometric relationship behind tan H and tan. So I'll leave that up to you. So this thing will again for lossless case evaluate back to the original expression that we had derived. So yeah, I'll leave this as an assignment to you. And now we can also compute the power delivered to the input of the transmission line by this expression over here. So we have the voltage and current at minus L. So remember we are keeping the load at z equal to 0 and moving towards the negative z for the generator. So the power at the input is calculated by this formula. So this is the expression of the power at the input, and again, the power delivered to the load is again keeping L equal to 0 over here. We get this expression. So so taking the difference, so the power lost from due to the losses. So the power in the input minus the power at the output. Um, we can calculate, and this is what we observe. So you can see that the first term over here accounts for the power loss of the incident wave, and the second term accounts for the power loss of the reflected wave. And both the losses increase as we increase alpha. Okay, so there's a question. If two conductors of a transmission line are very far apart, will C become vanishingly small? Um, so yes, so this capacitance of the in the upper two conductor transmission line is basically due to these two conductors, and the C will become vanishingly small. So, and okay, any follow-up question on that? Yes, so in that case, again, so beta will become zero and we won't have any propagation. So essentially, the transmission line won't be acting as transmission line because the two conductors are too far apart. So we won't have any waves propagating through it. Any okay. In that case, the two conductor. So okay, so DC will definitely propagate, and for considering AC, so AC will again AC will also AC can also propagate. Like I'll have to let me think. So if the two conductors are very far apart, second conductor is providing the return path. So if C is vanishingly small, so the Z, let's look at this way. So okay, okay. So let's take a look. Okay, so if C is very small, so this will imply this impedance will become very high, and and it will be inductive. So the yeah, so only DC. So the inductors actually block AC, and yeah, so yes, so only DC will propagate. Yes, and that is yeah. And any follow-up questions on that or what we covered till now? So that in the case of terminated lossy lines. Otherwise, we'll proceed to transients on transmission lines. So one more topic in the transmission lines, and then we'll start with the history of transmission lines and waveguides, and study about the T mode, TN mode. Thanks. So all these things. To the previous slide, everything is all normal. We are just replacing J beta by gamma. And over here, tan and J that okay, tan beta L by tan H gamma L. So this changes over here. Calculating the input impedance, so the power at the input over here and the power at the load, and so over here we try to calculate the loss, and this turned out to be this expression where the first term accounts for the loss of the incident wave, and this term accounts for the loss of the reflected wave. So that's what we have seen. Looking at transients on transmission line. So what happens if the like initially, for example, there was no wave propagating, and now suddenly you add a source to it. So as soon as the source is added, so what will happen? Over here, we'll look at a DC source being added to uh, the transmission line. So consider this particular circuit over here with the case that at t equal to 0, this particular switch is like turned on. So this is connected, and before that we do not have anything propagating inside the transmission line. Now, as soon as this circuit is closed, this voltage will propagate through this circuit. Now, what happens is this. If notice over that this generator, the input impedance of the generator is Z0, and again the characteristic impedance of the transmission line is also Z0, and the load impedance is also Z0. So we've seen that these two are matched, and if you are looking at this point over here, that Z input over here, this will turn out to be again Z now. So this voltage source will see these two things in series, and both with the same impedance, both equal to Z naught. So this will act as a power divider kind of circuit, and so the voltage will be divided across this particular resistor, the source resistor, and the transmission line. So we'll have V naught by 2 across this resistor, and V naught by 2 traveling through this transmission line. And uh, so this particular voltage will travel through the phase velocity Vp, and we can we can calculate with respect to time at what distance this voltage is traveling. So as soon as it is turned on, this transmission line will have V naught by 2 over here, and with Vp velocity, this particular voltage will travel towards the load. And as soon as this voltage uh, uh, hits the load, so this wave, this voltage will reach this load resistance at L a time instant L by Vp, and by till that time, this diagram will look like this, that we have at L where we have the load. So again, please take note that now we have switched to this axis over here. So now the generator is at 0 and the load is at L. So at L, before the this time instant L by Vp, this load will have 0 voltage over here, and the transmission line is still being like energized by this voltage V naught by 2. And after L by Vp time, so since this load is matched, so again this V naught by 2 will potential this voltage will be across this resistor again. And since both of these impedances are equal, so this will stay this way. So we will have V naught by 2 across this, and V naught by 2 across this throughout this transmission line, and again across this load as well. So after for the time, so between the time 0 to L by Vp, so we will have voltage versus the this put voltage versus the voltage across the transmission line length, looking like this. And after t greater than this particular time, the voltage will remain equal to V naught by 2 throughout the transmission line. This is what it is written over here. So initially, it is assumed that the voltage on the line is 0 for all z for t less than 0, and the switch is closed at t equal to 0, and the voltage. So again, this source will see this as a voltage divider. So and we will have V naught by 2 across this and V naught by 2 over here. And this will voltage waveform will propagate with velocity Vp, and the leading edge will be at the position of Z at this time t Z by Vp. And as soon as the pulse reaches the load t at t equal to L by Vp, since the load is matched to the line, there will be no reflection from this particular pulse, and we will have V naught by 2 and V naught by 2 on both the resistors. So this is the case for a matched load. So reflection of pulses from a terminated transmission line in case of a matched load, and this is how the transient will like propagate. So any questions on this? The next we'll see if this is what happens if this is a short circuit or an open circuit. Okay. So then maybe we'll proceed for the short circuit case. So similarly, again, we have the same circuit, just instead of the load, we have a short circuit over here. And again, at time t equal to 0, this switch is being turned on. So in this case again, so till figure B, it remains same. So until the voltage waveform reaches the load impedance, so this particular uh, voltage will propagate by V naught by 2. So because this is again the this particular voltage, this the generator is again seeing this as Z naught, and again Z naught indirectly over here, and this will propagate with again the same velocity. And as soon as this particular waveform will hit the short circuit, what will happen is this particular wave will be reflected back, and this will be so the this short circuit has a reflection coefficient of gamma equal to -1. So we will have a inverting phase over here, and this reflected pulse will travel back towards the source. So this is how it like so this dashed line till over here is what happens when it reaches the load impedance. And now as soon as it reaches over here, its phase is inverted, and it will travel like this. So taking a summation of the forward voltage and the backward voltage, what will happen is essentially what will happen is that the voltage will become zero, and this particular this v equal to zero will propagate with the same velocity. So for t less than L by Vp, we have this case over here, and for t between L by Vp and 2L by Vp, this particular we the reflected pulse will travel back, and we will essentially it will go towards the source and then short the source. So again, the superposition of the forward and reverse traveling pulse leads to the cancellation. So essentially, this was the forward and this was the backward way, and it is leading to its cancellation between the period L by Vp and 2L by Vp. And when the return pulse reaches the source at t equal to 2L by Vp, it will not be re-reflected because the source is matched to line. So again, the source has a input impedance. The source has a impedance of Z naught, and the line has a impedance of Z naught. So if you look from this direction over here, so this the source is matched to the line. So we will not have any reflection from this side. But again, from this side, we have the uh, and now when the circuit will be in steady state, we will have zero voltage everywhere on the line. So, and this also correspond to the simple circuit theory where if you have a source and it is shorted, so the so essentially you we do not have any the voltage throughout the circuit will be zero. The load also gets shorted. Yeah. So this is the case for a short circuit, and on similar lines, we have the open circuit as well. So just in case of the open circuit, what will happen is so this again open circuit also has a reflection. The open circuit has a reflection coefficient of equal to 1. So what will happen is that again the voltage will be reflected, but the phase will be same. So it will get added up, and so bit for 0 to L by Vp, this figure remains same, and for L by Vp to L by Vp, so this is what it looks like. So this will be traveling back towards the source, and these two pulses add, and we have V naught over here. So the total voltage will become V naught throughout the transmission line. So again, this matches to the circuit theory again, where if we have a source and it is left at the open circuit, so the irrespective of whatever the resistors there are, so we will have the between the open circuit, will have the potential difference equal to the source. And again, the same similarly to the short circuit at t equal to 2L by Vp, the reflected pulse will reach the z equal to 0, and it will not be re-reflected because this transmission line and the generator are matched. And in the steady state, throughout the transmission line, we will have a constant voltage of V0. So this is also very intuitive that for open circuit, the voltage throughout the transmission line should be V0, and for a short circuit, it should be 0, and for Z0, it should be V0 by 2. So even without mathematics, we can directly come to that conclusion. Now, so before we start bounce diagram, so again, I'll again pause over here and take any questions that you might have from the reflection of pulses from a terminated transmission line for the matched load, the short circuit, and the open circuit. Okay, so we'll proceed then. So another interesting way to depict the voltage across a transmission line is using bounce diagrams. So this might also come in. This is a popular question in especially in undergrad for your midterms and interns. So you can look into more problems on this. So this is fairly simple, and so we'll follow one example from Podzar, and you can find more examples online as well. So what we let's take this particular this we'll use this example to learn to draw a bounce diagram. So here is the circuit that we have for which we have to draw the bounce diagram. And the again this switch over here is turning at t equal to 0, and we have a source of 12 volts over here. The source resistance is 50 ohms. The load resistance is 200 ohms, and the characteristics impedance is 100 ohms. And we have denoted the reflection coefficient at the generator at gamma G, and reflection coefficient at the load as gamma L. And the source is at z equal to 0, and the load is at Z equal to L. So, and the questions ask us to draw the bounce diagram for the transient circuit of the figure, this figure, including the first three reflections. So, first three reflections we have to draw. So, yes, so we'll start with the solution. So the first thing we need to do is calculate the amplitude of the incident wave, which is given by this voltage divider formula. Uh, so this is a simple circuit theory thing. So we have to calculate the voltage that will be delivered to this transmission line over here. So this is 50, this is 100 using the voltage divider simplification. This and the this voltage over here is 12. So 12 into 100 divided by 50 plus 100, we get this as 8 volts. So 4 volts will be dissipated across this resistor, and 8 volts will be dissipated across the transmission line. Now the next thing is that the incident ray can be plotted as a line from. Okay, so we'll see the plot at this. Okay, so let's first calculate the reflection coefficient, the two reflection coefficients. So the lambda g can be calculated using this 50 ohm and this 100 ohm. So this turns out to be 1 minus 1 by 3, and this reflection coefficient over here can be calculated using 100 and 200. So this turns out to be 1 by 3. And now, okay, so let's see the bounce diagram again. So it says that the incident ray can be plotted as a line from the origin to point ZL, and T equals to L by Vp. So we essentially what we are trying to say is that at the load line, and we have to draw this axis at a load line, and we have the origin we already have one line, and we divide the time axis. So the time axis is along in this direction, and we'll divide the time axis by L by Vp. Okay, so so the L by Vp is the time in which the your wave will reach the end of the transmission line. So what we have done over here is that at the time, so we divide the time axis by L by Vp, 2 L by Vp, 3 L by Vp, and 4 L by Vp. This it is essentially giving us the time in which the your first wave. Okay, so let me use a pen over here. Okay. So it is essentially giving that so as soon as this switch was turned on, your voltage will travel from here to this direction over here in time L by Vp. Okay. Now again, this after reflection, this will travel back to this particular point, and this will reach over here in 2L by Vp. Okay. And now similarly, when it again reflects back and comes over here, it will come over here in 3L by Vp. So this is why for the time axis will mark the L by Vp, 2L by Vp, 3L by Vp, and 4L by Vp. And now what happens is that what I used to do is I used to draw a dotted line along this as well. So this helps me to keep track of things. Okay, so we have calculated that this particular incident voltage V plus, which will be equal to 8 volt, will travel from this 0 to L point within this time. So what we'll do is we'll draw this line starting from uh, 0 over here. So and this will by this particular time, L by Vp time, this will reach the low position of the load over here. So as where this intersects, we draw this line and we write 8 volts over here because this is the incident voltage. Now, as soon as this particular point hits the load impedance, we need to calculate the amount of voltage that is reflected back. So we can calculate the amplitude of the reflected wave using this expression over here. We have a reflection coefficient given over here as 1 by 3. So the voltage that will be reflected from the load will be 8 this 8 volt into the 1 by 3 over here. So 8 by 3 volts will be reflected, and this 8 by 3 volts will reach the again this generator at 2L by Vp. So we can draw with again this line over here. So we so we had 0 volts over here, and this essentially becomes 8 volts, and 8 volts travels from here to here. So we drew that line. And now, after reflection, this particular how much voltage will be reflected by 8 volt by 3. And when it reaches over here, again at this particular point, we calculate the amount of voltage which is reflected from the generator. So this turns out to be minus. We have to multiply it by minus 1 by 3. So 8 volt by 3 comes over here, and with the reflection coefficient is minus 1 by 3. So minus 8 by 9 volts gets reflected back. And now this will reach again the load at 3 LYBP. So we again join this line over here with and label it as 8 by 9 volts. And similarly, when it reaches over here, and again the reflection coefficient is 1 by 3. So this 8 by 9 volts into 1 by 3 volts will be reflected back. So again, this will reach the generator again at 4L by Vp. So this is how we draw a bounce diagram, and you can also calculate the at any point on the transmission line the voltage. So if you want to calculate the voltage at, for example, uh, this particular point is, is creating some trouble, Z1. So all you need to do is draw a line straight to this and add the voltages. So you have 8 volt over here. So and minus 8 bits, and using the time you can find that. So refer to Podzar. This I've already told you how to draw this bound diagram, and you can find rest of the things over there. So this is already given in great detail in Podzar. I don't know whether I'll be able to write a Podzar or not. Okay, but so I'm trying to write Podzar over there. So refer to Podzar. This is not that big of a deal. So I just wanted to touch this topic so that it's not left. Okay. So maybe if you have any questions, this is the last topic that we had to cover in from the transmission line theory, and we'll now move to transmission lines and waveguides. So where we'll see all the formulations using electric fields and magnetic fields. So if like any questions maybe that you might have from bound diagram, but I'll highly recommend reading both are. Okay. So yeah, maybe you can look at the book directly. So we'll start with the this new module now. So with starting with a little bit of history of transmission line waveguide. So microwave engineering started long back. We have already discussed a little bit about the history when we started with the electromagnetic theory in the first module. So one of the early milestones in microwave engineering was the development of waveguide and other transmission lines. So this allowed for low loss transmission of power at high frequencies. So and again, so again heavy side. So considered the possibility of propagating the electromagnetic waves inside a closed hollow tube in 1893. So in 1893 was the first time that we were trying to design waveguides, but he said rejected the idea because he believed two conductors were necessary for the transfer of electromagnetic energy. So again, so Heaviside rejected the idea of this waveguide thing, and now in 1897, Lord Rayleigh uh, proved that wave propagation in waveguides was possible for both circular and rectangular cross sections. So Rayleigh actually proved that even just with one conductor, structure could allow propagation of EM waves. And he also noted all the infinite set of waveguide modes, the T and TM type that were possible with existence of a cutoff frequency. So we'll look into the mathematics in the coming slides and the coming classes. And finally, but this was not experimentally verified, and the experimental verification was done by Southworth, Georgie Southworth at AT&T, and W.L. Barrow at MIT. So simultaneously, both these researchers uh, carried out the experiments, and so one of them, yeah. So okay, so not sure about Southwest. So again, so Barrow performed experiments using circular waveguides. So this was a brief history of the like development of waveguides, and now some salient points on waveguides. So the early RF and microwave systems relied on waveguides, this lines and coaxial lines for transmission. But waveguides had the advantage of handling high power capabilities. So this is why we use or prefer waveguides whenever we have like high the power of is very high. But if and we require low loss because it is all metal and the waveguides usually have air filled in them, so it has very low loss. But again, these are very bulky and very expensive. So the way since they are made of metals, so they will be very heavy. And again, making these waveguides are very expensive, especially for low frequencies. Again, they will become even bigger and yeah. So although the waveguides have some advantages, they also have some disadvantages. But again, for especially for military purposes and all, we again we use waveguides only. Now, the cheapest thing for transmission of an EM wave is using a two wire line. But again, they lack shielding, and for coaxial lines, they are shielded, but they are difficult to fabricate. And again, like you cannot use them to have microwave components on them. So the although these are cheaper, but again they have their own troubles. And recently, since we have also seen that a lot of things are done on the PCB, the printed circuit board, and for that we have what we call that planar transmission lines. And this transmission could be strip line, micro strip lines, slot lines, coplanar waveguides, and other geometries. So these are all planar kind of transmission lines and wave guiding structures. So and these are very popular because they can be directly printed on this PCB, and you can directly solder components on them. And so every electronic device that we might have, so all of it has a PCB, and they all have transmission lines inside them. So right now we have this is the planar transmission lines that were very popular, and now we also have planar antennas as well. So everything is on PCB now. And since all these can be fabricated on PCBs, and they are so they are very cheap, and they can be easily integrated with active circuits and diode transistors. They are also now very small, so they can all be printed on one board to form the integrated circuits. Now, over here, so for our discussion, we'll start with different types of wave propagation modes that can exist on a general transmission line and waveguide, and then go into the specific cases. So, the first case, so for transmission lines, what we they usually have two or more conductors, and they can support what we call as transverse electromagnetic waves. Now, so what is this transverse electromagnetic waves? So these are characterized by a lack of longitudinal field components. So So what we're trying to say is, let me use pen over here. So, for example, if a wave is propagating in this direction, and so the transverse components are usually perpendicular to the direction of the propagation. Um, so this is, for example, this is the your Z, and this is, I believe, this is X. Yeah, so this is X, and this is your Y. So this is X. X, Y. Okay, this should be Y. Y, and this is Z. Okay. Yeah, so this correct, right? Yeah. X, Y. Okay, no, I made a mistake. Okay. So this is X and this is Y. Sorry. So and if your wave is propagating in the Z direction, so the components in the direction of X and Y and whatever in between, so they are the transverse component, and the component of the field in the direction of the propagation, that is the longitudinal component. So the TEM waves are the waves in which we do not have any longitudinal field components. So, for example, if you have an electric field, so a wave is propagating with electric field E and magnetic field H, and again this will have EX, EY, and EZ components, and HX, HY, and HZ components. And if the wave is propagating in the Z direction, so when you EZ and HZ components will be zero. So that is so that will be a TEM wave. And now on the similar lines, if we have a single conductor, so we'll see that if you just have one conductor, the TEM waves cannot propagate. And again, on the similar lines, TE and TM modes are one, in which the transverse electric means you do not have the longitudinal component of electric field, and transverse magnetic means that you do not have the longitudinal component of the magnetic field. Uh, so this is the definition for TM, and TEM modes, waves. And okay, so maybe I'll again pause over here. So we briefly discussed about the history and current the type of things that are being used for waveguides, and the advantages and disadvantages, and the TEM and TEM definition for these terms. So, any questions on these? Yes, I see a message, Harika. Harika, you have said sorry, but okay, okay. You need me to repeat TEM and the TM. Okay, maybe I'll what I'll do is first discard all these markings and then again share. Okay. So maybe I'll use a pen. Yeah, I mixed this thing a little bit, the coordinate system. Maybe I'll do this again. So if I have, let's say, so this is my x-axis, this is my y-axis, and this is my z-axis. Okay. And for example, we have a wave which is propagating towards the z direction. Okay. Now, and again, so and the wave has electric fields Ex, Ey, and Ez. Okay. And similarly, we have the magnetic fields Ex, Ey, sorry, Hx, Hy, and Hz. So we have a total of six six field components, three electric field components, Ex, Ey, and Ez, and three magnetic field components, Hx, Hy, and Hz. And so all these components are required for a wave to propagate in the space. And now what happens is, if this wave is propagating in the z direction, and okay, so let me first tell about this. So the I hope you got this. So the fields which are in the direction of the propagation, and in this case for the fields Ez and Hz, they are in the direction of the propagation, and we have fields Ex and Ey, Ex and Ey, and Hx and Hy. So these are Ex, Ey, Hx. Okay, so this got scribbled. So Ex, Ey, Hx, and Hy are the transverse component because they are perpendicular to the direction of the propagation, and we have Ez and Hz, Ez and Hz are as the transverse component. Sorry, the longitudinal component, because they are in the direction of propagation. So for a TEM wave, what happens is the longitudinal field components, uh, they are zero. The longitudinal field components are zero. So in this case, if Ez and Hz are zero, the wave will only have Ex, Ey, Hx, and Hy terms, and it will be a TEM wave. Okay, so if you write the expression for any wave, if you are writing the field components, and if you notice that Ez and Hz are zero and the wave is propagating in the z direction, so you can conclude that this is a TEM wave. I hope that was okay for TEM. So if the uh, the field components in the direction of the propagation are zero, it is a TEM wave. Harika, can you confirm you followed a TEM?
Uh, Fine, thank you for repeating. Longitudinal fines is
Yeah.
okay. Can transverse waves?
Okay. Okay, so the transverse electric and transverse magnetic are on a similar lines. For example, if now we are just considering the electric fields over here. Okay, so if for a for the if you're just looking at the electric fields, so we will have the Ex component, Ey component, and Ez component, and the wave could be propagating in any of these directions. So we are for our simplicity, we're assuming that the wave is propagating in the z direction. And again, similarly, you will also have the magnetic field components. Okay, so Hx, Hy, and Hz. So what happens if uh, Ez is Ez is zero, but Hz is not zero. So this is not zero. So in this case, we call this as a transverse electric case, because the electric field has only the transverse components. Then the longitudinal component Ez is zero. And this is the case when Hz is not zero. Okay, so if Hz is not equal to zero, then we call this as TE. And if Hz is also becomes zero, then it will become again TEM. Were you able to follow this? Okay. And again, so I'll repeat the TM as well. So for clarity, uh, so for TM, again, you will have the electric field. This is taking time to write. Again, so again, in case of TM, what will happen is you will have the longitudinal component of the magnetic field equals zero, or you can also remember it like this: that the transverse magnetic means you will have transverse components of the magnetic fields non-zero. So the longitudinal component will be zero. So uh, so again, so Hz will be zero and Ez will not be zero. And in that case, it will be a transverse magnetic case. And if both of them again become zero, then it will again go back to the TEM case. So I hope this was okay. Okay, and if you have any more conclusions, I think a lot of textbooks write this very clearly, and you can also again refer to POSA. Just remember that the longitudinal components are the components in the direction of propagation. So this is the direction of propagation. Okay. My pointer is doing some funny business. Okay, so longitudinal components are the components in the direction of propagation, and the transverse components are perpendicular to the direction of propagation. So if you know if you can follow the meaning of the longitudinal components, you can these two statements will help you understand the TE, TM, and TEM cases. Okay, so I hope this was clear. If you need me to repeat this again, you can please let me know. Okay, so then we'll proceed. We have a little math today from this chapter, and we'll again revise that whatever we'll do now again in the next class, and start with the derivations for TEM, TE on all these cases from the next class. Okay, so but we will cover a little math today again from this chapter as well. So, for our agenda now is to find the general solutions of Maxwell's equation for these specific cases of TEM, TE, and TM wave propagation in a cylindrical transmission line or waveguide. Okay. Um, so this is what a transmission line or a waveguide will look like. So a transmission line must have two conductors, and a waveguide is again just has one conductor. So these are the two general cases, and you can see they have a arbitrary uh, like structure. So, but for our formulations, we'll take the symmetric cases so that it does not complicate the equations much. Yeah, and these structures are assumed to be uniform to have uniform cross section throughout, and they are assumed to be infinitely long. Okay, so in the z direction, they are extending to infinity. Okay, so these are the structures, and again, if we assume we have time harmonic fields, so we can write these fields with e power j omega t dependence, and we are assuming that again the wave is propagating in along the z axis. So the z direction is again the longitudinal direction, and x and y are the transverse direction. Now we can write the electric field and the magnetic field in these forms. So Ez and Hz are the longitudinal components. So this second part is the longitudinal component, and E bar and H bar, these are the transverse component, and E bar minus JB is denotes the direction as the wave is propagating in the positive z direction. Okay, so this is how we are writing the field. So need not worry. This is just a way of writing, and yeah. So assuming that the transmission and or waveguide region is source free, we can now write the Maxwell's equations curl form like this. So we do not we have omitted the source terms over here. So these are the so again without the source, the Maxwell's curl equation look like this. We have already seen this in the second module. Now, using this Curl's equation and with this e power minus j beta z dependence, we can break down this electric field and magnetic field into all these six components, which can we can write them like this. Okay, so this is so Ez, Dy, Hx. So this thing maybe you can try practicing by yourself. So all you need to do is like perform write this electric field in its vector form ex ey ez, and then perform the curl operation on the left hand side, and write the magnetic field again hx, hy, and hz terms. Then equate the x, y, and z components, and you will end up with the this six set of equations. So I leave this maths up to you. So, and this I think this is already this might be covered in the electromagnetic theory course. So this is not the only trouble over here is writing these complex things with subscripts and this do sign. That is the toughest part over here. Otherwise, this is not very complex. So just make sure that you're performing the curl operation properly. And now what you can do is the six equations can be can be solved for four transverse component fields. So what in terms of Ez and Hz. So what we are doing that, for example, if you assume that we know Ez and Hz, so what we can do is we try to find out the Ex, Ey, Hx, and Hy terms in terms of Ez and Hz. So we all you need to do is again substitute these expressions into one another, and you will end up with these four equations. So this will take some time. Try writing them down. If your institute believes in long questions, they might ask you this. So maybe you can try practicing. And over here, what one simplification that has been done is that we have written Kc over here. So this Kc square is equals to K square minus beta square. So we know we already know K and beta. So K is so okay. So K, as you can recall, is uh, yeah, so the K is the wave number from the previous instances, and beta is the propagation constant over here. Uh, and now Kc over here is the cutoff wave number. So we'll look into this cutoff wave number thing. Just remember that this Kc is cutoff wave number. So we'll do this again in the next class. So need not worry. Maybe, but I'm leaving this to you so that maybe you can try finding out the curl expression, and then trying to write Ex, Ey, Hx, and Hy in terms of the Ez terms. So this is only like hard work in mathematics, but you can try. Now, for the TEM waves, as we saw in the previous slide, that for the TEM wave, if the wave is propagating in the z direction, Ez and Hz terms will be zero. Now, if you look at this particular set of equation, so if you substitute the value of Ez and Hz equal to zero, all these terms come out to be zero. Okay, so this does not look practical. So if Ez and Hz are zero, then transverse fields are all equal to zero, and this Kc turns out to be zero because K naught square is equals to beta square. So this is an indeterminate result. So this does not give any popular clear conclusion. So what we do is we can return back to these six equations and then substitute, then apply this condition Ez and Hz equal to zero. Over here, we'll substitute the values, and okay. So okay, this is all that we're planning to. Okay, I leave it hanging over here. So in the next class, we'll substitute these values into these expressions and find out the expression for electric fields and magnetic fields and the solutions for TEM waves. So, okay, maybe if you have any questions, you can ask now, or you can also return to the textbook and read this thing. So this is all taken from Podzar. We have started with, I believe, chapter 3 of Podzar, and module 4 in our course. So you can look at that. Try writing these, deriving these expressions. It won't be much difficult, but we will definitely give you a lot of confidence. If you have any questions, if we can take that now, or regarding this part, we'll again cover in the next class. Okay, so today we covered these particular topics: lossy transmission lines and transients on transmission line from transmission line theory. And from the transmission line and waveguide, a little bit of history, and started with the general solutions. And the next class will again continue with the general solutions of TE, TM, and TEM modes, waves. Yeah, okay. So this is all that was planned for today. If you have any questions, we can. Okay, I've asked this again. I'll wait for some time. If no questions, then we can end today's class. Okay, so I believe maybe no questions. If you have any questions, you can reach out to me like directly on WhatsApp, or post it in the group, or put an email. And all that is fine. So I'll stop the recording.